Hello, it's just too hot to be programming indoors today, so I've come outside, into my garden. Anyway, in this video we're going to be looking at something that's become so ubiquitous you probably don't even realise that it's there. And we're going to be looking at panning and zooming. To demonstrate panning and zooming, I've created a small application in the console game engine, and it displays a grid at different spatial scales. I can use my middle mouse button to pick up the grid and move it around relative to where I've positioned the mouse cursor. And this is quite important, because it doesn't matter where I select the cursor location, the grid moves relative to where the cursor is on the screen. And this gives the really compelling effect that I have indeed picked up the screen space and I'm moving it around with my hand. It's a very tactile user interface tactic. I've also added the facility to zoom in and out, and we can see here, now the grid zooms a little bit strangely because of the very low resolution I'm using in this application, so you see the cells aren't quite the same size, but that's irrelevant here. What we do see is that the grid grows and shrinks. But most importantly, it depends where the mouse cursor is as to where the focus of the zoom point is. You can see I went to the top left there and I'm moving back out, and if I go somewhere down here in the middle, just move the cursor around so you can see it on the video, and it always ensures that the point you're zooming into remains in the same location. This is to avoid the user getting lost. It also doesn't matter how far zoomed in we are when we start doing pan operations. The same strategy still applies. And in fact, once you have established a suitable strategy for world space to screen space transformation, we can do everything through that transformation. So I can even select cells in the grid by clicking on them, and it doesn't really matter what the spatial scale or position of the grid is. And I can also move the mouse cursor whilst I'm zooming too. You get a slight rotation effect there. So let's have a quick look at what's going on, and we'll start with the easier one, panning. We've actually done panning several times before in previous videos. For example, the RPG series as the screen panned around, and the Jario platform game series. And both of those relied on a simple concept that we have a screen space where our top left is 0, 0, and we have some world space that represents the space we want to draw on the screen. I'll just draw that in green here. And the reason I'm drawing it off center like this is to make a point, but we can assume that the world space had a one-to-one relationship with the screen. So top left of the world space was up here, and we also knew that to be 0, 0. However, to pan this around, we needed to store two offsets. One which was here, which was offset X, and one here, offset Y. And so if we take a point somewhere in world space, let's say in this instance it's 10, 5, and we wanted to draw that in the corresponding screen space, which let's say for argument's sake is about here, then the translation was quite simple. We simply subtract the offsets from world space to screen space. So we go in the X direction and then again in the Y direction. Therefore, without any scaling, we can get some very simple equations that the screen space X location is equal to the world X location minus some offset X. And of course, exactly the same goes for the Y-axis. And we'll see this a lot. There's all these things happen to both axes simultaneously. And with some very simple algebra, we can work out the transformation between world space and screen space. So here, we've got world X equals screen X plus the offset. Simple stuff. We're going to be using these transformations so much that I really recommend that we have a world to screen function and a screen to world function. Let's start writing some code to see if we can implement panning. I'm going to start with an empty console game engine project, and this time I'm going to construct a console which is 160 characters wide by 100 characters high, and each character is 8 by 8 pixels, so it's reasonably low resolution. And in the onUserUpdate function, I'm going to draw a grid. But the first thing I'll do is clear the screen to black. If I want to draw a grid of 10 by 10 cells, I need to draw 11 vertical lines and 11 horizontal lines. I'll do this with a for loop, But this for loop, you may notice, goes to y is less than or equals 10, so this effectively gives us 11 iterations through the for loop. Each cell in my grid is going to be 1 unit across by 1 unit high. And because I want to keep this code as an example for others to easily follow and implement in their application, I'm going to be quite verbose with how I name the variables. And I'm leaving out a lot of optimizations. So for my line, I want to create a start point and an end point, designated by the SX and SY and EX and EY values here. And typically, what I would do is call the drawLine function to draw a line between these coordinates. However, we need to factor in our offset. So we'll come back to this in a little while. Somewhere in our system, we need to store the transformation variables. So I'll add two floating point values, f offset x and f offset y. I'll initialize those to 0 to begin with. And now I'll add my two transformation functions. So this is world to screen and a corresponding screen to world. So let's look at the arguments. I'm going to pass in a coordinate in world space, x and y. These will be floating point. But I'm going to return, via the arguments, the corresponding screen space coordinate. And these are integers, because our screen is discretized. Now we don't have any scaling at the moment, so what I'm going to do is just handle the panning. So we'll take our screen coordinate, and we'll need to cast that to an integer, because the operation is going to be performed in floating point domain. And I'm just going to implement the equations that we saw before. If I can type. There we go. And of course, we don't want both of these to be x, we want one of these to be y. In the same way, let's handle the screen to world transformation. This time we'll need to cast to a float our end screen variables. Let's go back to where we were drawing the grid now. What we can see is that the coordinates here are in world space. Each one of my cells is 1 by 1. I'm going to need to convert these to screen space. So I'm going to create an additional 4 variables which are the screen space equivalent of the world space variables. And then I'm going to call my world to screen function. Now all draw routines will only occur in screen space, so it's important that we use only the new variables to do this. And I'm going to draw the line as a solid white line. This code has handled 10 horizontal lines. Let's take the same code and repeat it. This isn't optimal. We could do everything in the same loop, but I'm trying to keep it as clear as possible, and we'll use this loop to draw 10 vertical lines. As you can see, the rest of the function remains unchanged. Let's take a look. Well, we see a rather boring white square at the top left of our screen. Well, that's kind of what we expect, because this square is 10 by 10 pixels. Because our grid was in unitary cell size, remember? And our offset is currently 0. So our world space is a direct mapping 1-to-1 of our screen space. In onUserCreate, I'm going to default our offset variables to point to the middle of the screen. So I'm going to take the screen width and screen height and divide it by 2. But I need to invert this number because the offset is negative. Because if we study our world to screen function, we're going to be subtracting this negative and adding it. Let's take a look now. So now we can see that the top left of our world space is mapped to the middle of our screen space. Let's push the drawing routines to the bottom of our onUserUpdate function. And given that this is going to be a heavily mouse-driven application, I'm going to capture the current mouse coordinates at the start of the routine. Of course, the mouse operates in screen space. So whenever the user clicks with the mouse, let me draw a crude mouse cursor in here, we need world space to be transformed around where the mouse has selected, because we want world space to always remain relative to where the mouse has been pressed. And to do this, we need to store some additional offset information from the top left of our world space to the current mouse position in world space. So we need to store this offset too. I'm going to call this startPanX and startPanY. And I only want to update these variables when the user presses the mouse button. So I'll add an if statement that checks to see, has my left mouse button been pressed? If it has, it captures the current screen space mouse coordinates and stores them in startPanX and startPanY. As the user drags the mouse, we want to update our offset positions to move the world around. So I'll respond to that on the beHeld flag. As the user drags the mouse around the screen, The mouse coordinates may change, but the start pan position doesn't. Therefore, we want to set our offset by the difference between the mouse coordinate and the start pan coordinate. I also need to now update my start pan location. So in between frames, it's as if start pan has been clicked each time. I should point out that it doesn't matter if you're using an event-driven framework. The concept is exactly the same. You just respond to your on-click and on-left up and on-left down or appropriate events. So let's take a look. We've got our rectangle in the screen, and it doesn't matter where I select with the mouse cursor, the world is translated into the screen relative to my mouse cursor. So let's try a really odd one down here, there we go. And of course let's try right in the middle of the rectangle. Very nice. And we should also handle something in the negative domain as well. So we know in our world space the current screen cursor will be in negative world space. And that works just fine. Let's put that back in the middle for next time. And that's all there is to panning. It's pretty simple, isn't it? However, zooming is a little bit more complicated. Zooming requires that we somehow scale the world space as part of our world to screen and screen to world transforms. So I'm going to store two additional variables, scale x and scale y, and by default I'm going to set them to 1. So that maintains our direct mapping between world and screen space. Now, to my shame, I have no mechanism for capturing the mouse wheel as part of the console game engine. I certainly will add that in the future. But typically you would want to use the pressing of the mouse wheel as part of the panning operation and the scrolling of the mouse wheel as part of the zooming operation. I'm going to emulate this with the Q and A keys being held down. So I want to zoom in, i.e. make things larger, when I hold down the Q key. And all I'm doing here is increasing the scale value by 0.1%. And on the contrary, if I want to zoom out, i.e. make things smaller, I need to decrease my scale value also by 1%. Different policies for changing the scale variables can be implemented here. In this instance, this is a very smooth scaling effect. You might want to scale in discrete steps. But the downside to this approach is it is effectively linear. So as you start to zoom in, you need to zoom in a lot more to see any difference on the screen space. But don't let that put you off trying this method. This gives a very nice feeling zoom. Now, as I've already mentioned, scaling is simply adding multiplication of the scaling value somewhere in our transform. And so when we're going from world to screen, once we've transformed the offset, we just want to multiply by our scale value. F scale x and F scale y. And if we do the algebra, that means in our screen to world transform, we want to divide by F scale x here and F scale y. If you're just starting out on your programming adventure, you always want to be careful when you see divides like this, because you might hit a divide by 0 error. However, we've ensured that that can't happen with the way that we're handling the zoom value. This can never be 0. Unless you're one of those people that would like to start arguing about the properties of floating point numbers. So let's take a look. Here's the grid, and if I press the Q key to zoom in, well, we see the grid sort of shoots off to the bottom right, and if I zoom out, it gets smaller and larger, so I'm confident that the scaling is actually working. But the position of where the scale is occurring around doesn't seem right. And that's because our scale is completely centered around 0, 0, and so the offset from world to screen space is also scaled. This isn't quite right. We can demonstrate this to be the case if I push our world space to be right up in the top left of our screen space. This will be approximate, and I choose to zoom in. We see it zooms in reasonably appropriately. But as soon as I start to pan things, it all starts to fall apart. It becomes very difficult for the user to use. Instead, I want the world space to scale around where the current mouse cursor is in world space. So here the black line outlines my screen space and the green line implements my world space before I have done a zoom. If I want to zoom around this location, so that's where my mouse cursor is, and I choose to zoom in, the effect that I want is that this point remains the same. Unfortunately, we already have the facilities to handle all of this, because if I know where my mouse coordinate is in world space before I zoom, it's here. After the scaling, my mouse coordinate has also been zoomed. And if we assume that scaling is happening around 0, 0, which it currently is, so my zoom has actually happened here. So my new mouse coordinate after the zoom is about here. Well, if I look at the difference between the pre-zoomed mouse coordinates and the post-zoomed mouse coordinates, I can create a vector which I can use to offset the new world space, because this vector will be the same as the vector that we need to displace the world. So before we do any zooming, I'm going to capture the mouse position in world space, and this is very simply done because we have the screen to world function. After the zoom, I want to do the same thing, but don't forget the scale has changed, so the internals of the screen to world function has also changed. And once I have the before zoom coordinate and the after zoom coordinate, I can subtract them and update the offset accordingly to displace the world around the mouse cursor. So let's take a look. Well, I'll start to zoom in now. Oh, it seems to be a bit juddery and all over the place. That said, it's not going completely out of control. It still doesn't feel quite right. Why might this be? Well, the answer lies here, and it's where we create the offset for the mouse. This currently only ever exists in screen space. We're not doing any scaling here. So I'm going to divide by our scale values too. And you might think, well, why was that necessary? Well, if you look at this, this is translating mouse coordinate differences into a world space offset. And so that's a screen to world transform, slightly different in this context. But we can see in our screen to world transform, we're also dividing by the scale value too. Let's try again. Well, it's still a bit jittery, but at least now the zooming is actually happening around the mouse cursor. And if I start to pan the scene, that works equally well too. So what's going on with this horrible jitter? And it doesn't take long for me to discover the problem. It's that I clearly don't know how to program at all. Here I'm casting this floating point calculation to an integer before multiplying it by our scaling values. I've got brackets in the wrong place. I need to enclose all of this calculation. And now you can see the zoom is very smooth indeed. Schoolboy error there, never mind. Well, that was all quite embarrassing, but whenever you see sort of jittering like this, that's usually a solid indication that there is an integer to float, or the other way round conversion, not happening quite as you'd expect it to. Now that we have working panning and zooming, we can start to do other operations using our world to screen and screen to world transforms. So the first one might be to actually select something in world space. I'm going to add the two variables selected cell X and selected cell Y. And at that location in world space, I'm going to draw a red circle. So after I've drawn the grid, I'm going to transform the selected cell in world space to screen space. Don't forget my cells were 1 by 1, so if I want the circle to appear in the middle of the grid, I have to add 0.5 to it. In this instance, I also need to scale the radius of the circle, and I'm just going to use the X scaling factor to do this. Throughout this program, we've kept scale X and scale Y independent, and this would allow later on to scale independently in those axes. If you've got a plotting program, for example, that might be quite a useful thing. But in this case, I know that my scale X and scale Y always change as a pair, so I can take one of them. They always assume the same value. And now that I have my transformed circle coordinates, I can simply draw a circle in screen space. To work out which cell the user has selected, I need to take my mouse coordinate and translate it to world space. Now, I already have grabbing the mouse coordinate as the first thing that I do in my program, and I could probably get away with using that, but the most accurate mouse coordinate is now the mouse coordinate after any zooming has occurred. And so I'm going to set my selected cell coordinate based on my transformed mouse world coordinate after any zooming has occurred. I'm going to do this on a right click. Let's take a look. So I'll just zoom in a little bit here, and we can see in the top left we have a circle, crudely drawn, again low resolution, in the cell 00. And if I right click somewhere else on the grid, we can see it's working quite nicely. And of course I can pick it up and pan it and still select, and it selects the right cells. It doesn't matter what the zoom level is either, the transformation is fine. You can imagine this having lots of applications in level editors, image editors, and I think all sorts of different 2D applications. That's why this is such a useful tool to have in your programming toolbox. There are also a number of other optimizations we can exploit now. Now that we have a mapping between world space and screen space, why draw parts of the world that you can't see? How can we clip it? Well, I could very simply create 4 variables which represent the left, top, right and bottom of the world in screen space. And I use the screen to world function to take my top left coordinates and put them in world space. And I can do the same for the bottom right by using the size of the console. And I can use these values to decide what I draw to the screen or not. I mean, after all, why draw things that you can't see? So to demonstrate this, I'm going to keep a track of how many lines that I'm drawing with a lines drawn variable. If a line gets drawn, I'm going to increment that variable. And what we do for y, we'll also do for x. And because we've chosen a low resolution, means I can easily draw strings and we can read them at the same time. Let's take a look. So currently, all the lines of the grid are drawn. That's all 22 of them. But as we start to zoom in, we can see our lines drawn count is starting to decrease significantly. Let's get it down to just the 1. There we go. So we can optimize our rendering framework very nicely. In fact, you could take this further. At the moment, it's still testing all of the lines. That's not necessary either. Why not only start drawing from a location which you know can be seen? You don't even need to do the tests at all then. And finally, and very much just for showing off, I'll let you study this on your own time, we can also plot a graph. So let's make a lambda function which always returns the sinf function. The reason I'm doing this is we can easily change the nature of this function and explore it in different ways. Now this looks a little complicated, but I'll try and explain what's going on. I'm going to scroll across my entire screen, so I'm looking for all of the visible pixels from left to right in world space. And in order to do that, I need to know what my world space per screen pixel is. Because I don't want to draw things unnecessarily, but I want to draw things at high resolution as we zoom in. So calculating this screen width per pixel is not that difficult. I just take the world right and world left values that I calculated earlier and divide it by the screen width. That tells me how much world space is attributed to each pixel. I'm going to store 4 integer coordinates, which are my pixels to be drawn, which is the current pixel and the previous pixel, because I don't want gaps in my function either. I want it to draw a line between successive values. And this line here is just the very first value to draw, so it doesn't draw from 0, 0 each time on the function, it draws on the first visible valid location along the x-axis on the screen. So I'm going to loop from the left-hand side of the screen in world space to the right-hand side of the screen in world space. That's my x-axis. And for each valid location, I'm going to calculate the function. In this case, it's up here. In this lambda function, it's sine. And I'm going to offset it accordingly in world space. So my grid is effectively 10 by 10. I want to locate it to the middle of the grid. And don't forget, when we're rendering on a computer screen, positive y tends to be going down the screen. This is contradictory to mathematics as we know it, so I'm going to throw in a minus sign so that the sine function is the right way up. For each world space pixel, I'm going to calculate the screen space equivalent, and I'm going to draw a line. So let's take a look. And we can see here we've got something that looks crudely like a sine wave, but I need to zoom in. But it draws from the left to the right of the screen at all times. The nice thing is it doesn't draw beyond those locations. And I can zoom in, and zoom in, and zoom in, and the function never loses any accuracy. And I can also pan. So a little bit of a rush at the end there, but it shows you just how sophisticated having these very simple transforms can be. And so that's that, a very simple yet powerful programming tool to add to your programmer's toolbox. If you've enjoyed this video, give me a big thumbs up, have a think about subscribing. All of this source code is available on GitHub to download and play with. You should come along to the Discord server and have a chat. It's growing every day. And take care, I'll see you next time.